Thank you very much, Dasso, and thank you very much, John, for inviting me today. Shifting gears slightly towards climate and impacts on water security in East African drylands. So particularly, I'm going to talk a little bit about three projects, which are, so the work I'm talking about today covers or spans three overlapping projects that are ongoing right now, all with the aim of trying to understand how we translate climate into usable information on the ground for water security, and with an aim to really understand how the climate is affecting water resources and water security in the East African region. The grants are very multidisciplinary, involve social sciences. We do work on the ground with communities to understand barriers and opportunities for adaptation to climate. We do tool development, model and mobile phone app development. We work with policy and we collaborate with some of the big climate services providers in the East Africa region, particularly ICPAC, for those of you who are familiar. Our geographic focus is Kenya, Ethiopia, and Somalia and Somaliland. And so basically, to give you the context here, why is climate such an important issue in this region? Well, the reason is because a lot of the rural dryland livelihoods in the East Africa region are intimately tied to rainfall. So pastoralists and farmers rely on the consistency of the two seasonal rains that occur in the region for crop growth, for fodder production, for their livestock, and for the supply of drinking water resources. So basically, climate change can come in and disrupt systems that have been in place for thousands of years in terms of adapting to aridity in these regions. Communities have systems and strategies for dealing with low rainfall and for being able to maximize the impacts of the rainy season. But climate change has the potential to disrupt these well-established systems. And as you can see here on this image, on the left-hand side, we have the rainfall totals for June to September 2019 period, and on the right-hand side is the food security projection as well. And you can see that they're really closely mapped. So what happens to rainfall intimately affects water and food security in the region, with the potential to affect millions of people's lives and livelihoods. So there are challenges here with thinking about what is climate doing to the region, how is climate change going to impact these livelihood systems. And so if we look at the graph here, this is a historical record of rainfall anomalies, so whether rainfall is above or below a historical normal, where red indicates below normal, indicates drought periods, and blue indicates good or wet rainy seasons. And as you can see, in the last 4 decades particularly, droughts in the East Africa region have become more frequent and they've become more severe. And additionally, the recovery periods in between these droughts are becoming more short-lived and less frequent. The graph below that in brown indicates the corresponding increase in severely food insecure people in East Africa region. And you can see that that's climbing over time as well. So for example, over the last 20 years, there have been droughts in 9 out of those 20 years. So droughts are becoming the new normal, and this is disrupting the sort of livelihood systems that are going on. So for example, rain-fed agriculture, which you can see in a photo on the right-hand side, depends on the rainy seasons delivering consistent rainfall to match the crop growth cycle. Pastoralism, which is a big livelihoods industry in the East Africa region, also needs healthy pasture lands and surface water for livestock. And of course, humans and livestock require groundwater resources for drinking. So the question is, how is climate change going to disrupt the partitioning of water into these different sectors? So I anticipate a few challenges with climate impacts in East Africa region. I just want to go through to give a sense of what are the challenges with actually trying to anticipate the impacts. Well, so far, traditionally, predictions of climate and information about climate and forecasts really only based on atmospheric variables, what's happening to the rain, what's happening to the temperature. It doesn't tell us anything about what's happening to that rain once it hits the land. It doesn't tell us how that rainfall is translated and filtered through the land surface. Additionally, these regions in East Africa have a huge percentage of drylands. And in drylands in particular, the water balance, the way that water is partitioned within the surface, is sensitive not only to the total amount of rain that falls in a year or in a season, but to the actual rainfall characteristics, i.e., is it intense? Does it fall for a long period of time, a short period of time, and so on? So the actual rainfall characteristics matter. And a key hindrance in our current ability to predict climate impacts is that current models that translate climate into water do not represent the critical processes of dryland hydrology and the water balance. They have a humid region bias and exclude some very important processes that occur in drylands. And actually what we need is some projection going forward of usable and actionable information of water resources that people on the ground can use to make decisions about adaptation for their livelihoods. And of course, in the spirit of today's webinar, there is also the challenge of adapting to multiple hazards at the same time. For example, in the sense of climate, you have droughts and floods occurring simultaneously, and there are questions about how do people adapt to both. Now, I'm cognizant of I'm talking to predominantly potentially a geophysical community. So if you're unfamiliar with hydrological processes, I thought I'd give a little example of how humid regions and dryland regions vary, because drylands do have a distinct hydrology that makes the anticipation of climate impacts more challenging. So some of us live in Bristol where the rain looks like it does on the right-hand side. We may have days of light rain, but in dryland regions, we typically see seasonal rain. So it occurs concentrated in some periods of the year. And when rain falls, it falls as discrete, short-lived, and very variable rainstorm, often as a convective storm. And so for East Africa, for example, there are mostly two key rainy seasons: March, April, May, and October, November, December. And within these seasons, the rain falls, in short spurts, not continuously. And that sort of the way that rainfall is delivered affects the way that the water is then filtered through the ground into the different water stores. And another key difference is that rivers look very different. So on the right-hand side, the humid regions will have perennial flowing rivers where the groundwater table is close to the surface and provides flowing water all year round. In drylands, though, the groundwater table is quite deep below the surface, and some rivers, and most rivers, tend to be ephemeral or dry most of the year and flow when there's sufficient rain to produce runoff in the streams. Additionally, that runoff in the stream is a big source of groundwater replenishment in drylands. And one of the challenges is that dryland regions may see prolonged periods of drought, but punctuated by very destructive flash floods. And we can call this, or think about it, as a whiplash effect, where people are whiplashed between extreme drought and extreme flash floods. And they're certainly not mutually exclusive, and they certainly provide a compound challenge. So in our projects, we've developed a new hydrological model for drylands, which we want to use for climate services in the East Africa region. We call this DRIP, and it contains all the missing critical components that models currently do not include to translate climate into water. The first of these is that we represent spatially restricted and short-lived rainfall as storms in even hourly durations. We represent high losses of rainfall by evapotranspiration. These are hot regions, they have high evaporative demand. Lots of water goes back into the atmosphere after it rains. We simulate the very brief and spatially variable events, the runoff events that create this ephemeral drainage network, ephemeral flow in the channels. And we include a very important component, which is this recharge of the groundwater through losses in ephemeral streams or leaky ephemeral streams. And we include a two-way interaction between the groundwater and the surface water. And now, we feel like this is a crucial first step in representing that translation of climate into water. But the next step, of course, is thinking about how do we provide this in a way that's actionable by communities in the East Africa region. How do we link that to seasonal rainfall forecasts that are going on in East Africa? So what we have done, and we're in an experimental phase right now, is we linked our dryland model, which has been tested and calibrated and works very well for Kenya. We link this to the regional rainfall forecast provided by ICPAC, which is the biggest climate services provider in East Africa. And we link our model to their seasonal rainfall forecast to provide seasonal water forecasts. So what this looks like is like this. So on the right-hand side, you see a map of the East Africa region. It represents the forecast given by the Greater Horn of Africa Climate Outlook Forum, the GARCOF forecast. These forecasts are issued 3 times a year for the rainy seasons, corresponding to the rainy seasons of the region. And the forecasts are given as tercile probabilities of seasonal total rainfall, meaning that they will provide a probability that the rainfall is above normal, normal, or below normal. And these are based on climate models that are provided, objective climate model outputs. So we provided this as a pilot for a large basin, a 15,000 kilometer basin in Kenya, the Wassu-Nyiro basin. In here in red, you can see. And the tercile forecasts by the GARCOF were given as 50% for the upper tercile, meaning above normal, 25% for the normal, and 25% below normal for this season that we're just in right now, the March, April, May season. Now, as you can see from this map, the granularity is pretty low. So for the entire blob where you see the green, that's the forecast, but we don't really know what that means for water on the ground. And as I mentioned before, the subtlety of how rain is expressed in different regions, how it's filtered through the ground, varies quite enormously. So we take the GARCOF forecasts and we combine them with our hydrological model using sub-daily rainfall and provide a pilot forecast of water for that basin in Kenya. The way that it's done is we link that tercile rainfall to potential hydrological outcomes. To do this, we run historical simulations of the hydrological model using all the historical rainfall data going back several decades. And then we create a lookup table where we associate the rainfall terciles to a range of probable hydrological outcomes. So we basically take the rainfall terciles and then we create a lookup table of corresponding hydrological outcomes. So in this case, you can see that we ran a whole bunch of historical simulations and then we put them in the terciles that correspond to the rainfall years. And this is done for river flow. Then based on the probabilities, the 50%, 25, 25, we resample and we create a water forecast ensemble, and we can do it for various variables that are important for plant growth, such as soil moisture, which affects crop growth and fodder production, groundwater recharge, which is important for drinking water and reserves, and number of days of extreme stream flow, which may affect flash flood probabilities. And we can obtain something like this, which has a lot more granularity than the GARCOF forecast, because it's run through a high resolution hydrological model. And you can see that, of course, the rainfall is one aspect, but filtering it through the ground provides more spatially explicit probabilities of soil moisture or extreme flow or groundwater recharge that takes account the kinds of rainfall probabilities, but also the conditions on the ground. And we can do that for the terciles, but we can also do that for physical thresholds. And we can say, well, what's the probability that you'll get more than 0 millimeters of groundwater recharge potentially, and you can get maps like this. And what is the probability that you'll get at least 1 day of extremely high flow in the rivers, and you can get maps like this. And you can see how the probabilities vary according to the structure of the catchment, as well as the rainfall probabilities. What we have done then is used this. We've implemented this as a demo into the East Africa Hazards Watch app, which is a desktop app that's hosted by ICPAC. It includes loads of different hazards. If you haven't explored this already, it's got things about floods and food security, tropical cyclones, temperature, rainfall, etc. And we're currently piloting it for our catchment, for all the hydrological variables of the water balance, soil moisture, extreme stream flow, and so on. And the idea is that we will extend this to the full East Africa region by next year, because we are now in the process of creating a regional water balance model. So we're basically upscaling our DRIP model to encompass a full regional simulation. So once we do that, that will be embedded as part of ICPAC's Hazard Watch app, and will provide seasonal water forecasts for the entire region of encompassing Somalia, Kenya, and Ethiopia. So just to end the talk there, I just wanted to reflect on this notion of multiple hazards, and particularly thinking about the context of climate and climate change. So the idea that we've heard some very interesting talks already by Juliet and John and his team about the earthquake hazards and the volcanic hazards. And then superimposed on that, we have a climate which provides incredible challenges to the region, and climate change, which has a potential to disrupt existing systems and can lead to multiple and compounding hazards. So in the photos on the bottom, you can see just examples from the last year or so. The region has suffered both droughts and flash floods, both with associated with loss of life and livelihoods. And additionally, a locust infestation, which is one of the largest in 7 or so decades for Kenya at least, which was a result of the sequence of drought and wet years. So following a long period of drought, there was a very wet year, which created this breeding of infestation of locusts. And these kinds of compounding climate hazards will become more common into the future. And the challenge for adaptation to the region is dealing with these multiple climate hazards, often contradicting in their nature for the people living in the regions, and have serious consequences for health, water systems, food systems, natural ecosystems, and of course, resulting in ongoing on downstream impacts on conflicts and migration in the region. So if we were to add all these to the geophysical hazards just mentioned, we are really in a region that is dealing with extremely high level of multiple hazards at the same time. I'll stop there. Thank you very much. If you want to find out more about what we do, the team is very large. I think many collaborators, postdocs, and collaborating institutions. There are too many names to mention here, but you can find more about our research on those websites. Thank you very much.
Thanks very much, Katerina. Really exciting work and very useful. I'd love to have one question from the audience, even though the time is really pressing. I will leave just a few seconds. In the meantime, can I just ask, how easy is it to extrapolate your seasonal and regional model for water forecast from Kenya, let's say, to a nearby region? What are the challenges in doing so?
The challenges are the same that we're facing right now. It's data availability and making sure that we have a robust and trustworthy model. So one of the key things is to test and make sure that the model provides reliable outputs for the region. But in sense of applying it to somewhere like Malawi or anything like that, the challenges are the same as what we face for the region, and it's very doable if we have all the data layers that are required of the model. And I see that the idea is that we can transfer this to any region that we want.
That's really great. I'm sure that you will be happy to answer questions if they arise in the chat in the following. So may I thank you once more for this presentation.